Hey everyone, it's Sophia, and today I would like to talk about a formula that's often regarded in complex analysis as a fact. However, this formula is not so trivial. With some help from Dr. Azoff and what we've learned with the Dirichlet functions, I was able to find a Calc 2 motivation on why this Euler formula is true. So first, I would like for us to recall that e to the x is the summation of x to the n over the factorial. This is a Maclaurin series, power series, centered at 0, therefore Maclaurin. This sum, when written out term by term, is a little bit easier digestible. Next, I would like for us to recall cosine of x is also a power series. Written out term by term, it's also a little bit better to digest. Next, recall sine. And now this is where we can just take our e to the x, and everywhere we see x, we can replace it with I to the x. So our sum looks a little bit like this. We can factor out I squared because it's just -1. So our sum looks something like this. And once we factor out all of our I squared term by term by term, we can see that we get something like this. So 1 plus ix minus x squared over 2 minus all this rest of the stuff. If we notice, there's only certain terms that have I in them, which can be explained by the formula that only I is present in the sign. So this is the real part, this is the imaginary part. So let's look at our formula again. So we have this. We have a real part, and we have an imaginary part. We have a real part and an imaginary part. Real, imaginary. This goes on and on and on. But what we see is that the real part in this equation stems from the cosine, and the imaginary part stems from the sine. And if we multiply sine by I, this Maclaurin series by I, we would get this term, and we would get this term, and we would get that term. So if we just kind of pull out what we want, we would get this going to cosine, this also going to cosine, this going to cosine. All the even powers would be a part of cosine, and all the odd powers would be a part of sine. And I think that proves that this formula is tricky to understand, but very beautiful.